Good morning. I'm MRP Arvasari, E20025. Today I will present my individual research project on improved feedstock blending strategies for biomass power plants. My project is supervised by Ms. Peradeniya. This study focuses on optimizing fuel mixes for a biomass power plant with considering affected factors for the power generation. This is the contents arrangement of the presentation. So according to that, we can move on to the introduction part of the presentation now. Biomass is a versatile renewable resource derived from wood and agricultural residues. In a power plant, these materials are combusted to generate high pressure steam for electricity production. However, the efficiency of the process is highly dependent on the quality and consistency of the feedstock. Let's we discuss about the problem statement. Currently, biomass plants face significant operational hurdles when using diverse feedstocks. There is a fuel vulnerability because relying on a single source like paddy husk leads to shutdowns during seasonal shortages. Furthermore, significant energy variance across different biomass types causes unstable furnace performance. Without an optimized blending ratio, we see unburned carbon particles and high fuel wastage. My project addresses these issues through four main objectives. First one is property mapping. From this case, we are characterizing the high heat value, moisture and ash for 8 specific biomass types. Second one is chemical assessment. We are doing for this to identify slugging components relative to boiler limits. Because of the availability of the time and resources, I decide to go maximum 10 points. It means every sample pair mixing with 10 different mixing ratios, and from there we can get suitable mixing ratios. Finally, creating a strategic screening tool to find the best fit pair for optimum operation. In my literature review, I analyze the core scientific reasons about the renewable energy feedstock. Rice husk has high ash content and low energy, while wood chips offers much higher energy density. Past research proves that mixing these two linearly increases the high heating value and improves the overall quality of the fuel. Critically, for our boiler, both wood and husk have over 65% of volatile material. This ensures that the fire stays stable even at our restricted boiler temperature limits. Furthermore, blending acts as a chemical shield. It dilutes the high silica in rice husk, keeping the alkyl index low enough to protect our furnace grades from melting ash and clinkers. Finally, adding wood improves bulk density, making the fuel easier to store and feed into the system compared to the pure loose husk. Now we are going to look at what are the gathered knowledge gaps through the literature review. First, we know how wood burns and how rice husk burns individually. But we don't have a clear map of what happens when we mix them in different amounts. We need to know the exact sweet spot for these 8 specific materials. Most research papers talk about very hot furnaces, but when our condition, our boiler is limited to 450 Celsius. So we don't know yet which blend will stay lit and burn completely at this lower temperature without wasting fuel. And also there is a lack of quantitative data on the alkyl index for blending ratios, leaving the furnace great vulnerable to high silica melting and clinker formation. My methodology is divided into three main stages. First one is sample preparation, where 8 biomass types are ground and homogenized and have to do approximate analysis. In this case, I have to look at the availability of each type of material because the most of proportion of uses biomass is Glycidia and it mathematically more than 50%. For then second one is the weighted screening. This is an innovative scoring matrix where I have evaluated HHV, cost, ash and the alkyl index like there are several factors we have to compare each other from using this weighted screening method. And also finally I'm trying to make a 10-point blend testing. Measure the HHV of 10 different ratios using the Bob calorimeter to find the maximum energy of this each pair. When we consider the feasibility of this project, there we can see three main feasibilities. One is high heating value we can conduct using the Bob calorimeter and the determination of moisture, ash and volatile material of each sample can be executed, and the grinding and homogenization of the raw materials to required particle sizes for testing is feasible. This is my updated timeline. Because of the unavailability of the samples up to 8th week, I am unable to start my lab testings. So I have to extend my literature review up to 8th week and I have to start the lab testing from the 8th week. Thank you.